Microwave Tubes, Reflex Klystrons, Part 3, Series on Microwave Engineering, Lecture number 4.23. Reflex klystron is an oscillator. It is a microwave tube. Its power output is small, hence it is suitable for low power applications. It is also a low efficient or inefficient device. In practice, its efficiency can hardly be 17 or 18%, even less. It has several applications in the laboratory, microwave laboratory of the educational institutions. This device is commonly found as a source in the microwave bench. Mode of the device is an important aspect. This device can be operated in several modes. The frequency of operation of the device, it can be varied or changed. That is, the device has or it is associated with certain type of tuning facility. Repeller voltage is the parameter which is used most of the times to change either the mode of the device or to change its frequency of operation. Mode and frequency, they are also dependent upon accelerating voltage. The interconnection between repeller voltage, accelerating voltage, mode number, frequency of operation, it is described and discussed in the present session. In addition, an account of electronic admittance and admittance spiral, Rieke diagrams, all these aspects are also introduced, described and discussed in this third session, last session on reflex klystron oscillators. Now let us move further to the core of the session. Repeller voltage can be used to change the mode, to change the frequency, and also to change the power output of the device. Therefore, repeller voltage is a critical parameter as far as reflex klystron operation is concerned. Making necessary changes with the repeller voltage in the operation of the device is called repeller control. The basis of repeller control is the interconnection between repeller voltage, mode, frequency, power, etc. The interrelation between various quantities of operation of the device, it can be shown, it can be found in the form of an analytical relation. V are equal to square root of 8m by E, F L by N, square root of V0 minus V0. VR stands for repeller voltage, M stands for mass, E stands for charge over the electron, F frequency, L length of the repeller region, N mode of the device, V0 is accelerating voltage. From this relation, an expression for N can be found. It is square root of 8m by E, FL, square root of V0 by square root of divided by VR plus V0. By doing some differentiation, one can also get a relation describing frequency variation with repeller voltage as dF by dVr equal to 1 by 2 pi d omega by dVr equal to 2 pi n by 4 pi L square root of E by 2m V0. These two equations, they have a lot of importance, significance in the operation of the device. First equation says by varying VR, V0 or both, one can operate the device in any mode we want. Second equation, this one, dF by dVr. It says changing VR, varying VR, repeller voltage. We can change the frequency of operation of the device. In this diagram is shown graphically the relation between repeller voltage and anode voltage. Repeller voltage, anode voltage, these are different voltages. By varying either one of these two or both, one can drive the device into different modes of operation. This particular aspect is illustrated here. N equal to 2 means N capital N equal to 1 3 by 4. N3 means capital N equal to 2 3 by 4. One can notice lower order modes require higher repeller voltage. 1 3 by 4 mode requires more repeller voltage than 2 3 by 4. Another aspect that is apparent, one can easily notice, is lower modes, they also require higher anode voltages. To set 1 3 by 4 mode requires more anode voltage than the mode 2 3 by 4. Some more points which we can know from this graph, they are given in due course of time in the present session. Here is shown two graphs, one graph in A, one graph in B. A is frequency dependence on repeller voltage, B is power output dependence on repeller voltage. Now one or two points regarding A. The amount of frequency variation in lower order modes, it is less compared to the frequency variation possible in higher order modes. If you consider 3 3 by 4 mode, frequency variation is huge, whereas in 1 3 by 4 mode it is less. This is one aspect. Another aspect, power availability in lower order modes is high when compared to higher order modes. Here power available is large when compared to power available in higher modes. Also, one can notice power output is 0 for certain ranges of repeller voltage. For example, in between, we can call it 370. In between 370 and 690, let us say this is 690. In between these two repeller voltages, there is no output. The device is not at all giving out signal. You can find other ranges of repeller voltage too, where no power output. Some more points regarding repeller control we discuss now under observations. Certain regions exist in repeller voltage range in which there is no power output. Maximum power output mode is 1 3 by 4. At higher modes like 2 3 by 4, 3 3 by 4, the maximum power that can be realized is less. We have already seen, we have already understood while watching the previous slide. Repeller voltage range over which 1 3 by 4 mode exists is larger than that of any other mode. Voltage range of mode is smaller at higher modes like 2 3 by 4 and 3 3 by 4. The rate of frequency change with the repeller voltage is lowest for 1 3 by 4 mode. Even though this mode exists over a larger range of repeller voltage, its frequency range of operation is the smallest of all other modes. At higher modes, rate of frequency change with the repeller voltage as well as frequency range of the mode is large. Now we move to another aspect pertaining to klystron oscillators, electronic admittance. The electronic admittance of the reflex klystron is defined as the ratio of the induced current I2 to voltage V2 across the gap. And these two quantities, they are to be considered at one instant. That instant is at t equal to t2. Here current means phasor current, voltage means phasor voltage. Mathematically, the symbol for this quantity is YE. E stands for electronic. Y stands for admittance. It can be shown equal to 2I naught beta I J1 x prime e power minus j theta naught prime by V1 e power minus j pi by 2. It can be manipulated to give I naught by V naught beta I square T naught theta naught prime to J1 x prime by, in the denominator apart from V naught we have 2, we have x prime 2, whole thing multiplied by e power j pi by 2 minus theta naught prime. Here beta stands for beam coupling quotient. J stands for Bessel function of the first kind. 1 is order. X prime is bunching parameter. Theta naught prime is transit angle of the electron in the repeller region. V1 is amplitude of the voltage across the gap. Now, oscillators including reflex klystrons, they are feedback amplifiers satisfying unity loop gain. In case of reflex klystrons, for unity loop gain, the magnitude of the negative real part of electronic admittance should be greater than or equal to the total conductance of cavity circuit. Mathematically, magnitude of minus GE, it should be more than G, where G is GC plus GB plus GL. C stands for copper losses, B stands for beam loading, L stands for load. These are components of equivalent circuit of reflex klystron. This is as far as G is concerned. And what is GE? GE is real part of YE. Electronic admittance is a quantity that plays a key role in the design of reflex klystron oscillators. Almost all oscillators are feedback amplifiers. A feedback amplifier goes into oscillations only when minus beta A is 1. It is called Barkhausen criteria. This criteria has to be satisfied by the klystron, reflex klystron, to if it is to give oscillations. The criteria applicable in case of klystron oscillators, it takes the shape of minus GE magnitude should be more than or equal to G. Now we move to admittance spiral. Admittance spiral is a graph. It is a graph between GE, real part of electronic admittance, and BE, imaginary part of electronic admittance. GE on horizontal axis, BE on vertical axis. If the relation is sketched, we get a spiral. As far as this diagram is concerned, 2 points require to be understood without miss. What are they? The total region of the graph, it is divided into 2. One is termed as oscillation region. Another is termed as non-oscillation region. Non-oscillation region may correspond to the region where that unity loop gain condition is not satisfied. When GE value lies in non-oscillation region, unity loop gain condition is not satisfied. Only when GE is in the region, oscillation region, condition is satisfied, and for that values of GE only, oscillator is able to give microwave signal. These two regions are separated in the diagram by a broken line. This is the broken. This is one aspect. Another aspect that should not be missed is, notice the point against which n equal to 3 by 4. This is the point. What is the location of this point? It is in a non-oscillation region. Hence, 3 by 4 mode is not possible. 1 3 by 4, n equal to 1 3 by 4. You can notice it is in oscillation region. 2 3 by 4, 2. So minimum possible mode in klystron oscillators is 1, 3 by 4. Some more points regarding electronic admittance. The minimum value of mode number at which oscillation can takes place is dependent upon the value of conductance of the cavity circuit. Its minimum value in practical oscillators is such that oscillations are not ordinarily observed in the mode for which n equals 3 by 4. Hence, the lowest mode that can occur in reflex klystrons is 1, 3 by 4. Here, specifications of a commonly found reflex klystron, they are given here. The specifications of 6940 Bendix type TK58 reflex klystron designed for use as continuous wave power source over 8.5 to 9.66 GHz appears as. These are specifications of Bendix reflex klystron. The maximum ratings are resonator voltage 350 volts DC, reflector voltage minus 350 volts DC, filament voltage 6.3 plus or minus 8% volts, gun cathode current 32 milliamperes DC, diode voltage of 350 volts DC, heater cathode voltage of plus or minus 100 volts DC. Typical operating conditions of this device are frequency 8.5 to 9.66 GHz, resonator voltage of 350 volts DC, reflector voltage minus 95 to minus 350 volts DC at 9.66 GHz, filament voltage 6.3 plus or minus 8% volts, gun cathode current 32 milliamperes DC maximum, tuner diode current 5 to 36 milliamperes DC and a tuner diode voltage of 170 to 25 volts DC. These specifications give some idea regarding different voltages that are required for the operation of klystron, along with their ranges too. Now, a few points regarding Rieke diagrams. What are Rieke diagrams? The frequency, output power, and efficiency of tube oscillators like reflex klystron. They are dependent upon operating voltages, currents, and also on magnitude and power factor of load admittance. Frequency is an important parameter. Output power is an important parameter. Efficiency is an important parameter pertaining to oscillators. These parameters actually define the performance, overall performance of the oscillator. These are dependent upon voltages and currents. They also depend upon load. Oscillator behavior can be represented graphically in several different ways, but two types of diagrams are highly useful and are therefore used exclusively while working with tube oscillators. One type is performance chart. Other type is load admittance diagram. Performance chart depicts the manner in which oscillator performance is affected by operating voltages and currents at a constant load. So, performance chart gives a graphical form description of dependence of frequency, output power, efficiency on voltages and currents at a constant or fixed load. The second one shows the manner in which oscillator performance is dependent upon the magnitude and power factor of load admittance under constant operating conditions. Here, operating conditions mean voltages and currents. Rieke diagrams are basically load admittance diagrams. So they describe the performance dependence on load admittance. They give contours of constant power or efficiency and contours of constant frequency plotted in polar coordinates against load resistance and load reactance. Note that performance charts are of greatest value for magnetrons, whereas Rieke diagrams are widely used in case of reflex klystron oscillators. As we are right now in reflex klystrons, our interest is mainly on, or our interest should be mainly on Rieke diagrams. Here is shown a typical Rieke diagram. We can notice BL by Y0. It stands for normalized load susceptance. Here is shown GL by Y0. It stands for normalized load conductance. One can notice constant power lines. So this is a line. It indicates, or it is for 550 milliwatts of power. Another line is there for 750, then 850, then 950. One can also notice certain lines, broken lines, for different frequencies. Here is shown one broken line against which the number plus 5 megacycles is indicated. Another broken line against which 10 megacycles is indicated. Another broken line 15 megacycles. Similarly, on the right hand side, you can find negative frequency changes, decrements, frequency decrement. So these are features of Rieke diagrams. These are some of the things which I want to share with you for right now. Hope you have enjoyed the session. Also hope that it is an enriching learning experience. Enough for now. See you again in another session. Bye bye.